In this video, we're going to show one relationship between the concepts of prime and irreducible, and that is we're going to show that every prime element of an integral domain is irreducible. The converse is not true, and we'll talk about an example later. So first of all, let me just state the theorem here. The theorem is exactly what you think it is. Theorem P, an element of R, is a prime, then P is irreducible. All right, so if P an element of R is a prime, then P is an irreducible element of R as well. So this is one of those places where I would actually recommend stopping the video and just take a stab at proving this. Because I think that trying to prove this theorem actually reinforces some really crucial skills for mathematical proof. So we're going to show that if P and R satisfies this definition here, then it also satisfies this definition. And the way that we do that is we assume that P is prime, so we assume this, which means that we get all of these things that are essential for knowing that P is irreducible. So P is non-zero and P is a non-unit. Note that an element has to be non-zero to be irreducible or prime. So these are satisfied automatically. These come along without any trouble. The main thing that we need to prove is this piece right here, that if P is equal to a product of two elements, one of those elements is going to have to be a unit. All right, so how do we approach that just from a generic proof point of view? We are given that this is true. This is part of what we get to assume. So we know that whenever we have P dividing a product of two elements, P has to divide one of those two elements. That's something that we know is true. And somehow we have to prove this statement here, this implication that if P is equal to a product of two elements, then one of those elements has to be a unit. So the way the proof is going to unfold is we're going to assume this in order to prove the other part. And the strategy for proving that is going to be to try to get ourselves into a situation where we know that something like this is true. Maybe with the two elements A and B that are part of our assumption, or maybe with something else. But either way, we're going to try to get to the point where we know this, because once we know this, given that we're assuming this implication here, if we know this, then this follows. So once we have P dividing a product of two things, we will know that P has to divide one of the two things. And we hope that at some point that will allow us to prove that one of the two things has to be a unit. Maybe not the one that P divides, but one of them anyway. So that's the strategy of the proof. Let's see if we can pull it off. All right, so first of all, since P is prime, we know that P is non-zero and P is not a unit. Great. So we need to show that if P is equal to A times B, where A and B are elements of R, then A is a unit or B is a unit. And our strategy is going to be to try to get it back to something in this form. Try and relate the situation that we have to a situation where we have P dividing a product of two things. So actually, here we're in luck. This is perfect because if P is equal to A times B, then that means that P divides A times B because P divides itself. So since P is equal to A times B, we know P divides A times B. And if you want to be really pedantic about why that's true, that's because P times something, namely 1, is equal to AB. So we know that P divides A times B. So since P is prime, P divides A or P divides B. So now we have two cases to address. So let's assume P divides A. Okay, if P divides A, then what does that mean? Then we know that A is equal to Px for some x in the ring. Okay, but let's think about that for just a minute. We know that A is equal to P times something. We also know that P is equal to A times something up here. So I can substitute for P the product AB, and we get A is equal to ABx. And at this point, Well, look at this. This means that A is equal to A times something. If we have A equal to A times something, then I can rewrite that as A times 1 equals A times Bx. And since A is non-zero, well, why is A non-zero? Otherwise, P itself would have been 0. Because P is a product of A and something else. So A has got to be non-zero. So since A is non-zero, and we're in an integral domain, we can use multiplicative cancellation to get that 1 equals Bx. And so now we know x is the multiplicative inverse of b, therefore b is a unit. Okay, so I did promise that when we were looking at this overall game plan here, we would probably at some point assume that one of these was true, or not assume, we'd be able to conclude it from the fact that p divides a times b. But knowing that p divides a would not necessarily lead to a being a unit, it actually leads to b being a unit. And we should kind of expect that, because if you're divisible by a prime, you're probably not going to be a unit. Okay, so anyway, that's case 1. And case 2 is really just the same thing, just with a and b reversed. So I'm just going to say same reasoning. If p divides b, then a will be a unit. Therefore, we know that p being equal to ab for a and b in the ring, that implies a is a unit or b is a unit. And therefore we are done. I don't know if that's what you came up with. You might have had a different approach here, but I think that's a pretty elegant proof. So now we know that anytime we have a prime element of an integral domain, that element's also irreducible. But as pointed out before, the converse is not true. Stay tuned.